Hello everyone. So now we will study the concept of CMOS inverter. So many people who prepare for analog domain specifically, they ignore this topic and say that it is asked in digital interview only. But no, even for the analog inputs, you can analyze this circuit, right? It is basically a circuitry, and it has also a high gain. We will see the gain of it. So it has also a high gain. So this is used in analog industry. Okay. So CMOS inverter is important topic. Okay. So now first we will see what is a buffer and what is an inverter. So what is the main difference between those two? So basic difference we will see. Let us assume this is a buffer. Okay. This is how we make a buffer. So this is how we make a buffer. So in case of buffer, if you give a high input, you will get a high output. Okay. And in case of buffer, if you give a low input, you will get a low output. This is what a buffer is. Okay. I'm talking about a inverter. So this is how you make an inverter. Okay. Yeah, so in case of inverter, if we give high output, we get if we give high input, we get low output, and if we give low input, we get high output. This is the case of inverter. Okay. So now we will see CMOS inverter. So first we will analyze the CMOS inverter for pulse input. Okay. So what is the circuitry of CMOS inverter? That we will see. This is the PMOS, and then in series with the NMOS. Okay. So this is the circuitry, and both have a common input. Okay. Both have a common input Vin, and this is VDD. From drain of NMOS and from drain of PMOS we get the output. Okay. So this is the circuitry of CMOS inverter. And what will happen if we interchange the PMOS and NMOS? It will become a buffer. I will upload that video. Okay, no problem. I will upload that video. If we interchange it, what will happen? That we will upload. Okay. Now the input is pulse, right? So we will make a pulse input. Okay. So like this is time 0, this is t by 2, this is t, this is 3t by 2, this is 2t. And one thing is that t is very large. That would be given. Okay, t is very large. And one input what we can put is 0 volt. One input we can put is 0 volt, and one we can put is VDD. Okay. So we will analyze it now. So for analyzing, I will use. So for 0 to t by 2, 4 times 0 to t by 2, what is your Vin? Vin is equals to 0. Then V, in case of PMOS, if you see, your VSG would be VDD, right? And in case of output, we can connect a capacitor. Okay, here in the output we have some load, that is a capacitor. Okay, so that we have connected. So what is VSG? VSG is VDD, and what is your VSD? That is equals to VDD as well, because your drain is at 0 potential. VSD is at VDD only initially at t equals to 0. At t equals to 0. Okay. So here this VSG is greater than VTP, right? VDD, like the value is not given, but you can take Okay, let VDD equals to 5 volt, VTN equals to mode of VTP equals to 1 volt. Okay, so VSG is greater than mode of VTP. That means it is on and in saturation region. Why in saturation region? Because VSD is greater than VDD minus VTP. Right? VSD is greater than VSG minus VT. Then it is on and in saturation. And in case of NMOS, at t equals to 0, in case of NMOS at t equals to 0, VGS would be 0 only. That means it is off. So your PMOS is on and your NMOS is on. So NMOS is off. So for 0 to t by 2, your PMOS is on and your NMOS is off. So if you draw the characteristics, now what we can write is initially PMOS is in saturation region. Okay, so what happens is that PMOS can be replaced with current source, right? PMOS can be replaced with the current source, and NMOS will be open circuited. This will be open circuited. So now what is the situation is that whenever a device is on, whenever a MOSFET is on and it is in saturation region, it will be replaced with the current source. And whenever it is in a linear region, it will be replaced with the R own resistance, right? R resistance, right? We know that, right? R own resistance. Okay. So now this is replaced with the current source, and at output we have this capacitor C, right? This is V naught, this is the capacitor C, and this is open circuited, right? This PMOS, this is PMOS, and this is your NMOS, right? And this is VDD. Now whatever the value of this current source is, that will charge this capacitor, and the capacitor will start charging. The capacitor will start charging linearly. Okay, so the capacitor will start charging linearly. Initially it will charge linearly. Okay, so this is your V naught versus time t curve. Now it will charge, it will charge. Now at one point V naught will reach 1 volt, right? And this is 5 volt. In this case your VSG is fixed. Your VSG is fixed at 5 volt, right? Your VSG is fixed at 5 volt, and your V overdrive is VSG minus VT. It means 4 volt. Now your V naught is getting up. That means your VSD is getting low. If your V naught is getting up, your VSD is getting low. When V naught equals to 1 volt, when V naught equals to VT, or when V naught equals to 1 volt, your VSD would be equals to 4 volt, right? Your VSD would be equals to 4 volt. So after that, it will go into the saturation region. Now V naught is increasing. That means your VSD is decreasing, but V overdrive equals to VSG minus VT P, that is equals to 4 volt, is fixed. That means, and PMOS is moving towards what? Moving towards linear region, right? Linear region. Okay, your V naught is increasing, that means your VSD is decreasing. That means your V overdrive is fixed. That means if it is moving towards the linear region. Okay, so it is moving towards the linear region. So when we, so at point of at VSD equals to VSG minus mod of VTP. Okay. So what is your VSD? VSD is VDD minus V naught. Your VSG minus VT is 4 volt. So VDD is 5 volt. So V naught would be equals to 1 volt. Okay. So when V naught is greater than 1 volt, at that time your VSD is less than VSG minus VTP. That means at that time linear region. We are moving towards the linear region. And if we are moving towards the linear region, that means PMOS will be replaced with R ohm, right? So this will be replaced with some R ohm value, and this is VDD, and no comments about PMOS, NMOS because it is still off, right? So this is V naught and this is like this, right? Here I can write NMOS is still off. NMOS is still off. Okay. So now it will charge exponentially. So exponential charging is there. Okay. So instead of making this curve here, I should have made it on next page, but forget that, we have written the explanation. So after this it will charge exponentially. So I can make it look like this. And till what voltage it will charge? It will charge till VDD voltage, right? So from 0 to VDD it will charge. And this is what is we don't know the value of time, but we know that this is the value VT, right? When V naught is equals to VT over 1 volt, here we have seen. After that we are going into the linear region. So this is the linear region and this was the saturation region, right? So you understood this. But in many of the book or in many, even in the interview, if you say that the PMOS is on, so it will be replaced with the resistance, so we will see exponential charging of capacitor. So even that would be that they will also consider. If we see deeply, we see that initially it is linearly charged. After that, it is exponentially charged. Okay. So, but in the interview, they don't notice this much. If you say that it is charged exponentially, then they also consider it. So this is what is happening. For a very small region, it is in saturation region. Then it goes to linear region. Now for what? For T by 2 to time T. Your V in is 5 volt, right? For T by 2 to time T. Your V in is VDD. That means V in is 5 volt. So now for PMOS, your VSG is 0 volt. That means it is off, right? So PMOS is off. And for NMOS, what is your VGS? That would be 5 volt. What is your V overdrive? V overdrive is 4 volts VSG man. And what is your VDD? ds, that is equals to v naught. Okay, and currently at t equals to 0, at t equals to 0, your vds is v naught, that is equals to 5 volt, right? Because it has been charged till 5 volt. It has been charged till 5 volt, right? So at t equals to 0, at t equals to 0, vds is 5 volt. So at t equals to 0, your vds is greater than v overdrive. That means it goes to saturation region. Okay, so NMOS will be replaced with current source, right? So your NMOS will be replaced with the current source. So this is the PMOS, that is open circuited. This was VDD. Okay, now this is the capacitor there. Okay, this is V node and this is the current source, right? This was already charged to VDD, that means 5 volt. Now the current is flowing in this direction. So this discharges the capacitor linearly. That means your V naught goes down. Okay, so your V naught goes down. So that means VDS for NMOS goes down. If it is goes down, that means NMOS is moving towards what? Linear region. That means when VSD is less than V overdrive. So what is VSD? That is V naught. That is less than 4 volts. Then we will move to linear region, right? So how will the output look like? What I can do is that I can simply copy this one and I will paste it here. So first what is happening is that it is linearly coming down, right? So from 5 to, from VD to, from VDD to, it comes down to VDD minus VT, right? VDD minus VT, and then if it has moved to linear region, then NMOS will be replaced with R own, right? So there will be exponential discharging. This is charged to 4 volt. This is replaced with R on. Okay, and this is open circuited, and this is VDD. Okay, so this will get discharged. From 4 to 0 we will go, but exponentially this time. So this is how it goes to 0 volt. And now the same cycle goes on. Okay. This is time t. Then again the same cycle repeats. again charges, then linear, uh, then this is in the saturation, and then it comes to the linear region. Okay, so this same cycle goes on. So from this to this, we have, this is the saturation region and this is the linear region. Okay, so this is the complete analysis. But in the interview, if you say it gets exponentially charged and it will get exponentially discharged, then they can somehow consider it. But if you tell this, first it will be in saturation, then it goes to linear region, then it comes down. So this is the exact analysis and this is the correct analysis. Okay, so now you have understood this concept, and there can be few more questions. Okay, so what they can do is that I will add on these question, those question. So what they can do is that they will make the same CMOS inverter. This is V in, VDD. This is also V in. Okay, I am just making it separately, nothing else. This is your V out. This is grounded. Now what I have done is that I have connected one more NMOS in parallel. Okay, you know what does this sign mean, right? I have told in one of the video, I guess. Okay, what does this sign mean? The same potential V, this sign really means like this. Okay, the same potential V in is applied there, so we can make it like this as well. To make the circuit look less complex, we make it like this. So this V in is applied here as well. Okay, so this is what it means. And now this is the capacitor C. So now you need to comment on capacitor charging and discharging. On capacitor speed of charging and discharging. So tell me the speed of charging and discharging, how it will change. First we talk about the speed of charging. When the capacitor is charging, that means your PMOS is on. Your PMOS is on. So there is only one PMOS. So there is no change in the speed of charging. Speed of charging remains the same. Now coming to the speed of discharging. So in case of one NMOS, we have two NMOS now. If we have two NMOS, so in saturation region, we will have two current source. If we have two current source, that means we will have more current. So more current will be coming out of this capacitor, right? In saturation region, we will have two current source. That means more current will be coming out of this capacitor. That means it will discharge fastly. So the speed of discharging is increasing. Or what you can see, in case of NMOS, when it is in triode region, it will be replaced with the R1 value, right? This will be replaced with R1, this will be replaced with R1. So what will be the time constant? Time constant would be R1 by 2 into C. Your time constant is decreasing. That means speed of charging is increasing. Time constant means whatever time it takes to reach some value, right? Whatever the time it takes to let us assume what is 3 to time or 4 to time. In 4 to time, the capacitor completely discharged. Okay. So if it is taking 4 to time, that means it will take 2 into R1C time. And before it was taking 4 into R1C time, right? So the time taken to get discharged is less. That means your speed of discharging has increased. Okay. So tau would be equals to R1 by 2 into C for discharging. That means speed of discharging has increased. Okay, so these kind of questions can be asked. Okay, So this is the complete analysis of pulse input. Now we will see the most important one, that is the ramp input. We will increase the value from 0 to VDD. We will increase the value of V in from V in of 0 to VDD. We will not directly jump from V in 0 to VDD. We will increase it linearly from 0 to VTN to VDD by 2, from VDD by 2 to VDD minus VTP, and then to VDD. Okay, so just you just need to have a strong concentration for that. Okay, so we will start it in next video. Okay, thank you. Hello everyone. Now we will see a very important topic, that is CMOS inverter with ramp input. Okay. So this is the input we have. This is the inverter that we have previously studied. So previously we studied about the pulse input. Now we will study about the ramp input. So this is the input we have. VDD equals to 5 volt. We are taking VTN. That means the threshold voltage of NMOS. VTP, that means threshold voltage of PMOS. That is equals to 1 volt. And we are increasing V in from 0 to 5 volt. So for better understanding, we are taking the value. But when we draw the characteristics, like in the previous video as well, when I drew the characteristics, I didn't write the values. Instead of that, I wrote the exact expressions, right? So now coming here in this one. Okay, so the first thing is that we will take V in to be 0 to VTN. Okay, from 0 to VTN we are taking. So when V in is less than VTN or greater than 0, that means here the value is less than VTN, less than VTN. Okay, that means your NMOS is off, right? NMOS is off and your PMOS is on. That means your NMOS, for NMOS we can write your VGS is less than VTN. That means it is off. That means it goes in cutoff region, right? And for PMOS, what happens is that your VSG is VDD minus VTN, we can write. Okay, no, VDD minus V in. Okay, VDD minus V in. So it is VTP is 1 volt. So it is surely greater than 4 volt, right? That means this value is greater than VDD minus VTP, VTN. That means it is greater than 4 volt. Okay, so it is greater than 4 volts. So that means your PMOS is on. Your PMOS is on and your NMOS is off. So now it is on, but it will go into saturation region or linear region. Just take your time and think about it. Saturation or linear. I will give you a hint. The current in both of the circuits would be the same, right? IDSN, ID, IDP I will write, and ID N I will write. So IDP would be equal to the IDN, right? This is the fact, right? IDP would be equal to the IDN. The same current is going. Now, if you say that there will be some load connected there, so that can have some current. Load will be very high. Okay, it won't take any current. So IDP would be equals to IDN. That's why I have connected no load here. Okay, IDP is equals to IDN. Okay, that is there. So just think about it. So what is your answer? It will be in linear region. Why so? Let's see. Sorry. This is our PMOS. So this is our VDD. This was our V in. And this is open circuited. Right? Your NMOS is open circuited and this is your V naught value. Right? And this is open circuited and this is your PMOS. Okay. Now the current in PMOS is 0. ID in P is 0 because the current in ID because the current in NMOS is 0, so the current here has to be 0, right? If the current has to be 0, then what? If we draw the transfer characteristics, ID versus VSG. Not VSG, ID versus VSD. So this is the linear region, right? This is the linear and this is the saturation region. So you know that current can never go to 0 in saturation region. So if your current is 0, there is no chance that it is in saturation region, because in saturation region the current is always greater than 0. So what? It has to be in linear region. Okay, because of 0 current. Right? So what did we see here? For 0 to V in to VTN. In this, what about your PMOS? PMOS goes in what? PMOS goes in cutoff. Sorry, not cutoff. PMOS goes in linear region, and your NMOS goes in cutoff region. Right? So this is our first point of analysis. Okay. Now we will move on to the second region. Now we have increased V in to be greater than VT. Okay. V in is greater than VT now and less than VDD by 2. Just forget about this VDD by 2. Just V in is increasing now. Now your V in is increasing from VT. So if V in is greater than VT, so in case of NMOS, what you will see? What is your VGS? What is your VGS? That is equals to VGS is equals to V in, right? In case of NMOS, your VGS is equals to V in. Now that is greater than VT. That means it will be on. If it is on, two question, saturation or linear. Okay, talking about the PMOS, your VSG is VDD minus V in. Now VT has just increased, so that will surely be greater than V overdrive, right? First it was 4 volts, VDD was 5 minus V in. VTP is just increased. Let us assume V in is 1.1 volt. Okay, V in is 1.1 volt. If V in is 1.1 volt, so it would be 4 minus 1.1. That means it would be 3 minus 3.9. And VDD by 2 would be 2.5. So 5 minus 2.5, that means 2.5. That is greater than, not V overdrive, that is greater than mode of VTP. Right? So that means it is also on. The question is saturation or linear. Right? Now both are on. And how I can write is as 5 minus 2.5 is always greater than 1 volt. I hope you will understand it. The maximum value is 2.5, so it will certainly be on, right? So now the question is both saturation or linear. Now both are on. Okay. So one thing I have told you is that whenever a device turns on, that means it will drive a very low current. Whenever a device turns on, it will drive a very low current. Okay, it won't take a very large current all of a sudden, so it will drive a very low current. So that means that That means that there is a very less current through the NMOS. If there is very less current through the NMOS, that means there will be a very less current through the PMOS as well. So whenever the device just turns on, I have told you this fact before as well. Whenever the device just turns on, it draws, not device, whenever the MOS just turns on, because in the transfer characteristics we can see that when VSG is just greater than or VGS is just greater than VT, there is very low current, right? This curve, this is very low, right? Or I can make it a bit properly. So this is your VT and this is your VGS and this is your ID. So if it is just greater than VT, so there is very low current. Okay. So whenever the MOS just turns on, it draws a very low amount of current. And previously your PMOS was in linear region. Your PMOS was in linear region. So by the previous analysis, what I will do, I will just replace it with the capacitor with the resistance. So this is R on and this is your VDD and this is your V naught. Okay, and this is some I can't say some current source initially. I will just make PMOS here. Okay, this is your V in. So if it is drawing a very less current, your V naught will ID is very less, very less. That shows that V naught is nearly equals to VDD at V in just greater than VT. Okay, like just initially, if your VT, if your V in is increasing from VT, from 1 to it is going to 1.1 volt, at that time ID is very less. That means the drop here is very less. At R1 resistance, the drop is very less. That means your V naught is nearly equals to VDD. So if your V naught is nearly equals to VDD, that means your VDS is very small. VSD is very small. So for PMOS, VSD is very small. That means it remains in linear region. For NMOS, what is VDS? That is V naught. That is nearly equals to VDD. That means it is very large, right? Or what is VSG? VGS. VGS is V in. Okay, and what is V overdrive? It is V in minus VT. So it is very low, right? Because V in is just greater than VT. Because V in is just greater than VT. Okay, at I should write at V in just greater than VT. Okay, at V in just greater than VT. Okay, so ID is very less at V in just greater than VT. So V naught is nearly equals to VT. That means your VDS is greater than V overdrive. So that means what? It goes in saturation region. Okay, did you understand it? Right? So for VTN, or VTN I am writing because VTN is a positive value itself. If I write if I write mode of VTP, that will also be fine. So for VTN to VDD by 2, your PMOS is in linear region and your NMOS is in saturation region. Okay, so I hope all this is clear to you. I will just repeat both of them, both of the condition once more. Initially what we saw is that your Vin is 0 to VTN. That means your NMOS is off. If NMOS is off, there is zero current. That means in the PMOS there has to be zero current. But in the saturation region, what we see is that there can't be zero current. So it has to be in linear region. So your PMOS is in linear region and NMOS is in cutoff region. When we increase Vin to some extent from VT, if Vin is increased from VT, that means your NMOS turns on and also your PMOS is also on. So if your NMOS just turns on, that means it will drive a very low current. If it is driving a very low current, that means your uh, PMOS will also drive a very low current. Now, since PMOS was in linear region before, we will try analyzing it by replacing the PMOS with a resistance, that is R1. So if we replace the PMOS with the resistance R1, then we saw that since there is very less current, so at PMOS there will be very less drop. So your V0 will nearly be equals to VDD. So for Vin just greater than VT, your V0 is nearly equals to VDD. So if that is nearly equals to VDD, then your VSD is very small. So for PMOS, your VSD is very small. So if VSD is very small, that means it remains in the linear region. Because if VSD is small, it remains in the linear region because we know the characteristics, right? Here we know the characteristics. If VSD is small, that means it remains in the linear region. And in case of NMOS, what is happening is that your VDS is equals to almost VDD and your V overdrive is just greater than 0, right? Because your V overdrive is V in minus VT. That is just greater than 0. That means it is very low. So your VDS is very, very greater than V overdrive, right? Your VDS is very, very greater than V overdrive. That means it moves to saturation region. Okay. So from VTN, so from VTN to VDD by 2, your PMOS remains in linear region and your NMOS remains in saturation region. Okay. So now what is happening is that now your Vin is increasing, right? Your Vin is increasing, right? We are increasing Vin from VTN, let us assume from 1 to 1.1 to 1.2, 1.3, 1.4, right? We are increasing Vin. That means VG, I will write VGS N is increasing, right? If it is in saturation region, NMOS in saturation region, no, it doesn't apply NMOS in saturation region. Your VGS is increasing. If your VGS is increasing, here I should write NMOS in saturation. In saturation, if your VGS is increasing, what is the current in saturation region? ID equals to some Kn dash VGS minus VT whole square. If this value is increasing, that means your current is increasing, right? Current ID N is increasing, right? If your current is increasing, that means current in PMOS is also increasing because both are connected in series, so the current there also should increase. That means your IDP increases. Okay, your IDP increases. So there is this current is increasing. Now what is IDP? IDP. This is in linear region, right? Till now it is in linear region, so it will be some kn k by kn. We can write it and kp. It will be some kp into vg vsg minus vt into vsd minus vsd whole square by 2, right? This is the value, right? Now in this one, what do you see? vsg is fixed, right? Just see here, vsg is vdd minus vin, not fixed. If vn is increasing, your vdd minus vin will decrease, your vsg will decrease. Vn is increasing, so your vsg will decrease, because this is fixed and this is increasing, so your vsg will decrease. That means your vsg is decreasing. Why so? Because vsg is vdd minus vin. Since vin is increasing, your vin is increasing, that means your vsg is decreasing, but your current is increasing, right? Here we saw that the current in NMOS is increasing, that means the current in PMOS has to increase as well, but your vsg is decreasing, so what has to increase? If this has to increase, so what value has to increase? vsd has to increase, right? uh, because this is in deep linear region, just ignore this factor, okay? Just ignore vsd square by 2. Just think about this factor, okay? Because vsd is very small, so we can ignore this factor. So if vsg is decreasing but id is increasing, but id in p is increasing, that means your vsd has to increase. If your vsd has to increase, that means your v naught goes low, right? Your v naught starts going low. vsd p. I will readjust these pages later on. So if vsdp is increasing, that means your PMOS is moving towards saturation, right? If your VSDP is increasing, that means your PMOS is moving towards the saturation region, right? Because if VSD is more than VSG minus VT, that means it is in saturation region. At some point, both PMOS and NMOS will be in saturation region. Look, this NMOS is already in saturation region. NMOS is already in saturation region. So if we are increasing V in, the current in NMOS is increasing, but the current in PMOS has to increase as well. The current in PMOS has to increase as well. But in PMOS, what do we see? If we are increasing V in, your VSG is getting decreased. If your VSG is getting decreased, then there has to be something that has to increase, and that value has to be VSD. So if VSD is increasing, that means the first thing you can see is that the V naught is going low, okay? And the second thing you can see is that if VSD is increasing, that means it is moving towards the saturation region. So NMOS is already in saturation region and your PMOS is moving towards the saturation region. So there will be one point where both of them will be in saturation region. and the current is already same. So your ID in PMOS at saturation region would be equals to your ID in NMOS at saturation region. So let's put both of them equal. So mu n mu p COX W by L, let us call this complete factor as Kn. No, Kp. Okay, if we are, but there is one thing we are doing wrong here is that if we are saying this is at K, this is at Kp, so I should write 2 Kp here. Okay, the Kp is mu n Cox W by L. Mu n Cox mu p. Mu p Cox W by 2L is Kp. Okay, mu p Cox W by 2L is Kp. Okay, so this is our Kp value. So Kp into Vsg minus Vtp mod whole square would be equals to Kn Vgs, oh, and this should be Vgsp, Vgsn minus Vtn whole square. This derivation is this derivation is asked many times. So what is Vsgp? That you should just keep in mind. What is Vsgp? That is Vdd minus Vin minus mod of Vtp Kn by Kp under root, right? We are taking under root on both sides, into Vgs, Vin. What is Vgs for NMOS? Vgs for NMOS, it is Vin into Vtn, right? So talking about what do we need to find? We need to find the value of Vin. So what we are doing is that we are finding the value of Vin at which we get both of them in saturation region. If both of them are in saturation region, so the current in both of them are same. So this should be, these two equations should be the same. In saturation region, the current will the current in both PMOS and NMOS are always same. Okay, and if both of them are in saturation region, we can put those current equals to 0. So from here we can get the value of Vin. So what we are seeing is that Vin minus Vtp plus root Kn Kp into Vtn would be equals to root Kn Kp Vin, right? Vin or Vi we should write if we are writing Vi here. So this is the value, yeah. So Vi would be equals to Vdd minus mod of Vtp plus root Kn by Kp into Vtn upon, there is something wrong I guess, Vin will come here as well, right? This Vin will come here as well. So upon 1 plus root Kp Kn Kp, 1 plus root Kn Kp. So this is the final expression, right? Okay, if mod of Vtp is equals to Vtn and Kn equals to Kp, then your Vin would be, this is equals to Kn equals to Kp, this will get cancelled. So and Vtp and Vtn are equal, so this will also get cancelled, this will become 1. So your Vin would become Vdd by 2. So this would be the switching threshold. Okay, we will talk about this point. What is switching threshold? At this point, both NMOS and PMOS, both NMOS and PMOS are in saturation region. Okay. So this we have seen is that there is one necessary condition is this: Kn equals to Kp. At V equals to VDD by 2, both PMOS and NMOS goes in saturation only when Kp is equals to Kn, right? That means your mu n COX W by L ratio of Kn equals to Kp, I will write, because I have written for Kn equals to Kp. Mu n COX W by L ratio of N would be equals to mu P COX W by L ratio of P. That means your mu n W by L ratio of P upon W by L ratio of N is equals to mu n by mu P. Okay, so this is one more important factor. So generally I guess most of you knows that generally the mobility of electron is more than the mobility of holes. Mu n is greater than mu p. The mobility of electron is more than the mobility of holes. A rough idea is mu n is almost equals to 2.5 of mu p. Okay, that shows that W by L of PMOS should be equals to 2.5 of W by L of N. Okay, that means PMOS if we want saturation region at V equals to VDD by 2, then W by L of P should be greater than W by L of N, and the rough margin is W by L of P should nearly be equals to 2.5 of W by L of N. That's why the size of PMOS is larger than, that's why the size of PMOS is larger than size of NMOS in CMOS inverter. Okay, so this question is asked many times, like why the size of PMOS is greater than the size of NMOS. Okay, now they can ask you more things like that. If you can write this expression, if you can remember, you should remember this expression as well. Okay, so if you can write this expression, they will ask you how you will change the value of V in, where this point is called switching threshold. Okay, why it is called switching threshold, we will see. So how can you change the point of switching threshold? Okay, so how can you change? By changing the value of Kn and Kp. Okay, so these questions are asked as well. Okay, and they can ask you more questions like that. If Kn is 4 times of Kp, then what will happen to the switching threshold? Okay, if Kn is 4 times of Kp, then just put down the value here. Assume Vtp equals to Vtn. Then if Kn is 4 times of Kp, then your VDD, let us take VDD equals to 5 volt. So it would become 5 plus 2 upon 1 plus 2. So it would be 7 by 3. And 7 by 3 is lesser than 2.5. So your switching threshold will decrease. And they can take other condition as well. Okay. If Kp is 4 times of that, then what will happen? 5 plus 1 by 2, 5.5 upon 1.5. 5.5 upon 1.5. What is that? That is greater than that is greater than 2.5. That means your switching threshold value will increase. So that's how you can change the value of switching threshold, by varying the value of Kn and Kp. Okay. So these questions are asked. These questions are very much asked. Okay. So you should uh, know this concept. Both are moving towards saturation, and at that point we just put the value equals to both of the value equal. Then we got this V in value. Okay. And then we just took this scenario because we are taking Kn equals to Kp. That means your V in is threshold. Uh, V in is at saturation at both of the NMOS and PMOS are at saturation when Vin is equal to VDD by 2. Okay. So this is the condition that we are taking. So we can write when Vin is equals to VDD by 2. Now we will write it later on. So since PMOS is in saturation region, okay, and NMOS is also in saturation region. Okay. So for PMOS, what is VSD? VSD. What is VSD for PMOS? VDD minus mode of minus V in. And what is V overdrive? That is VSG minus mode of VT. This is VSD minus V naught actually. VSD is VDD minus V naught, and that is VSG minus VTP. And what is VSG? VDD minus V in minus mode of VTP. At saturation, what is happening? VSD is equals to V overdrive, right? So VDD minus V naught is equals to, at saturation, what is the value of V in? It is VDD by 2, right? So it is VDD by 2 minus mode of VTP. From here, what is the value of V naught is coming? That I need to write. So where I should write it? I will just shift it upwards. Okay. So here your V naught value is coming to be VDD by 2 plus mode of VTP, right? So we know the V in value. So since V in equals to VDD by 2, we have saturation region. So just we put V in equals to VDD by 2 here, and just go to know what is the value of V naught. That is VDD by 2 plus VTP. And in case of NMOS, VDS is, what is VDS? That is V naught. What is V overdrive? V overdrive is, what is V overdrive? VGS minus VT. VGS is V in minus VTP. And at saturation, VDS would be equals to V in minus VTP. V in is VDD by 2 minus VTP. Okay. So this is the condition here and this is the condition here. Now at V in equals to VDD by 2, we are getting two outputs. V naught equals to VDD by 2 plus VTP, and V naught equals to VDD by 2 minus VTN. So what would be the value of output? Both of them will be there. So how will the curve look like? So for this much characteristics, we will draw the curve now. Okay, for this much value. So how it started? Initially it was at V out was at VDD, right? Talking about V out versus V in. So till this point, this was VT, and we can say. So did we discuss the value of V naught here? We should have discussed the value of V naught, because if this is if this is just off, right? If this is off, sorry, if this is in linear region and this is off, okay, it is on and it is in saturation or linear, so it is in saturation region. So there is no current across it. So there is no current across the resistor. So V naught is equals to VDD only. V naught is equals to VDD only, because we can replace this with the resistance. So V naught is equals to VDD. If we replace that with the resistance R on, so there is no current across that resistance. So V naught is equals to VDD, right? So V naught is equals to VDD here. So we should have written it here. V naught equals to VDD, right? And in the second case, what we have seen is that in the second case, if we are increasing the value of V in from VTN, your V naught goes down. That means your V naught goes down, right? So your V naught is starting to go down. So after that, your V naught is starting to go down. Now at VDD by 2, what is happening? This is VDD by 2. So at VDD by 2, what is happening? Right in the middle. Not this, this. So if this was VDD, okay, after that it was decreasing. So at VDD by 2, there is some point, this is that point, and this is that point. So at some point we have, this is the middle point. Here we have V naught value equals to VDD by 2. At this point we have value equals to VDD plus mode of VTP. How it came VDD by 2, that I will tell you. And at this point we have VDD by 2 plus VTP, and here we have VDD by 2 minus VTN. We just took the average. Take average. So V naught average would be VDD, both addition by 2. So it would be VDD by 2. So basically at V naught equals to VDD by 2, what is happening is that we have output equals to VDD by 2 plus VTP as well, and output equals to VDD by 2 minus VTN as well. Okay. So this kind of output we have, and also the average that value will be there. So whenever they ask what is the output at Vn equals to VDD by 2, we will say VDD by 2. Okay. Just the average we will say. So the curve is looking something like this. Now it will go like this. So the curve, nature of curve ahead we will see. So now the analysis will be very easy for you. Why? Because you have seen everything related to this. Now analysis should be easy for you. So the third one is, no, the next condition is, are we putting the numbers? No, we are not putting the numbers. So now your Vin is greater than VDD by 2. Your Vin is greater than VDD by 2, but lesser than VDD minus mode of VTP. I am not going to the inverter circuit again and again, but I hope you are understanding it. Okay, I think we don't need to draw the circuit again and again. Okay, for this one, because it is too long, I guess I should redraw it now. We can take it, right? So now your Vin is basically greater than 2.5 volt and less than 4 volts, right? So if it is less than 4 volts, this will be on, because 5 minus 4 will be greater than 1. 5 minus 3.9, it will be greater than 1. So here your PMOS is on, and also your NMOS. That means if it is less than 4, if it is greater than 0.7, it will be on. So it is less than 4. So your NMOS is also, right? So again that question, region, what is the region and what is the region of operation, right? So for PMOS we can see, and here we can write the region of operation as well. So I will put this VDD here. So here your PMOS was in linear region and your NMOS was in cutoff region. Here your PMOS was in linear region and your NMOS was in saturation region. Here your PMOS was in saturation region and your NMOS was in saturation region. Okay, now we will talk ahead. So for PMOS, you will try writing VSD. What is VSD? VD minus V naught. Okay, what is VSG minus VT? That is equals to VDD minus V in by 2 minus Vt, right? Let us take V in equals to 3 volt. Okay, so 5 minus 3 by 2 minus 1.5 minus 1, so it would be 2.5. Okay, and VSD would be 3 5 minus some V naught. V naught would be lesser than 2.5 only, right? Because V naught is decreasing only. V naught is decreasing. Why so? If V in is increasing, that means the current here is increasing. If the current here is increasing, that means the current here also increases. But here VSD is decreasing. So if VSD is decreasing, then VSD has to increase. So if VSD is increasing, that means the PMOS is moving towards saturation and the value of V naught is decreasing. The same concept that I have explained before. Or there is one more way to analyze it that we will also see. First thing what I am saying is that Vin is increasing, IDN is increasing, IDN is increasing, that means your IDP is increasing. If IDP is increasing, that means one factor has to increase, but VSG is decreasing. If VSG is decreasing, then VSD has to increase. VSD has to increase. So if VSD is increasing, that means it is moving towards saturation. So your PMOS is in saturation region. PMOS is in saturation region. Okay. Now your V naught is decreasing. Your V naught is decreasing. That means your VDS of N is going low. Talking about NMOS, if we talk about NMOS, V naught goes low. That means your VDS of N goes low. That means it moves towards what? Linear region. Right? So that shows that your NMOS is in linear region now. Basically, it's an inverter. Okay. If you have seen the characteristic till now, P was in linear, N was in cutoff. P was in linear, N was in saturation. Though both in saturation. Now what will happen? N will go to linear, P will go to saturation. Inverted. Okay. N will go to linear and P will go to saturation. Okay. And simply by concept as well you can see, right? If the current is increasing, VHD has to increase. And if VSD has to increase, that means V naught has to go low. And if VSD is increasing, that means it is PMOS goes to saturation region. And if V naught goes low, that means your NMOS goes to linear region. Okay. So for V in equals to VDD by 2 to V in and VDD minus mode of VTP. What is happening? Your PMOS is in saturation region and your NMOS is in linear region, and your V naught goes low. Right? So this is what is happening. Okay. Now we will see the last condition. What we could do is that we could have seen the this condition before as well. Okay. This is the last condition. Now your VDD minus VTP. Okay. And lesser than VDD. Okay. So now basically your V in is between 4 to 5 volt. Right? See this. Here if we have 4 volts, and here if we have something greater than 4 volt, let us assume 4.1 volt. So your PMOS will be off and your NMOS will be on. For 4 volts it will be on, but this PMOS will be off, right? At 4.1 it will be off. So PMOS will be off and your NMOS will be on. Now what will be the region of operation? Tell me. Linear, right? Because the current is 0, ID n equals to 0 is possible only in linear region, right? So for this condition, VDD minus mode of VTP to V in less than VTP VDD, at that your PMOS goes in cutoff and your NMOS goes to linear region. Okay. And what will happen to V naught value? V naught nearly goes to 0. Why so? Because this will be replaced with the resistance, right? And there is no current in that resistance. So V naught goes to 0 only. Did you understand it? This will be replaced with the resistance only. This will be replaced with the resistance, and at this resistance we are nearly having zero current. So V naught goes to 0 only. Okay. So V naught nearly goes to 0. Okay. Now we will draw the transfer characteristics. Complete transfer characteristics we will draw now. So from this curve we can pick it up. This is not that straightforward analysis. Okay. So now drawing the complete characteristics. So this point will be VDD by 2. No, not VDD by 2. It would be VDD by 2 minus modo VTP. Okay, then it goes down to 0. So it goes down like this, then it goes down to the same kind of curvature we need to make, and then it goes down to 0. Okay, okay. So in this region your PMOS was in saturation and your NMOS was in linear region, and in this region your PMOS was in linear region and your NMOS was in cutoff region. Okay, I hope you have understood the concepts now, right? And there is one more way of looking at the looking at this region. Okay, this second region, in this region when it was saturation and linear. So if we try to do the analysis from backward side, okay, we are trying to do the analysis from backward side. So let us assume we are going from 4 volt to just 3.9 volt. We are just going from 4 to 3.9. At 4 volts, at 4.1 volt it was off. Now we are going at 3.9. So it just turns on. The PMOS just turns on. That means the current is very low. And since this is already in linear region, so it will drive a very low current. That means it will have a very less voltage drop. If it is having a very less voltage drop, that means V naught will nearly be equals to 0. V naught will nearly be equals to 0. Yeah, right. Look, from 4.1 to we are going 3.9. That means the PMOS just turns on. That means there is very low current, and the NMOS can be replaced with the resistance. That means that resistance will have a very less voltage drop. That means V naught will nearly be equals to 0 volt. If V naught is nearly equals to 0, that means your VDS is very low in case of NMOS, and in case of PMOS, yeah, and is in case of PMOS, your VDS is very large. So if your VDS is, in case of PMOS, your VHD is very large. So in case of PMOS, if your VHD is very large, that means your PMOS is moving towards saturation and your NMOS is moving towards linear region. So from the previous analysis, we can see at 4.1 volt, NMOS is PMOS is off, NMOS is on. Now from 4.1 we are going to 3.9. So the PMOS just turns on. If the PMOS just turns on, less current in PMOS and less current in NMOS. Less current in NMOS, that means NMOS will have lesser voltage drop. If the NMOS is having lesser voltage drop, that means lesser voltage of V naught value. V naught value is less, that means V naught is nearly equals to 0. That means your VDS for NMOS is very less. If your VDS for NMOS is very less, that means it is in linear region. And your VHD for PMOS is very large. If your VHD for PMOS is very large, that means it is moving towards the saturation region. So this is one more way of analyzing the circuit. Okay. Now we have seen the voltage transfer characteristics. So this is VTC. This is voltage transfer characteristics. Now we will see current characteristics. Okay. So in the next video we will see. Just revise it once again, whatever I have taught. Okay. Not too much straightforward. What they will ask you from this, they will just ask you the region of operation. Just tell me the region of operation. That's it. That's it they will ask. Okay. And also that Kn Kp thing that I told. If Kn is greater than Kp, what will happen? The curve will move towards the origin. If the Kn is lesser than Kp, okay. So we can write one thing here is that Kn equals to Kp here. If Kn, in the formula we saw that if Kn is 4 times of Kp, 4 times of Kp, and Vt, and we will see it in next page only. Okay, so I have to draw 2 more curves, so that will be a good question. Okay, we will see it. Yeah, so we derived this condition, right? What was the value of V in for V in for both PMOS and NMOS being in saturation region? V in for saturation in both PMOS and NMOS. So at what value of V it goes to both NMOS and PMOS goes to saturation region. So this is what we call switching threshold. Switching threshold. Why it is called switching threshold? Because from here you can see is that the this characteristic and this characteristic is completely symmetric. After this point only, what is happening? The inversion is happening. Like N is saturation here and P is linear here. So after this point, P is saturation, N is linear. Here P is linear, N is cut off. So here P is okay. I wrote it opposite. Here your P is cut off and N is linear. So the inversion is happening, right? After this point only. So this point is known as switching threshold. This exact point is known as switching threshold. Okay. So when Kn is 4 times of Kp, we are saying 4 times of Kp, and for this curve we have seen Kn is equals to Kp, and one more assumption we have made is that your Vtn is equals to mod of Vtp. Okay, so we will take this Vtn is equals to mod of Vtp, and what when Kn is 4 times of Kp and Vtp is equals to Vtn, then what will be your V in? V in I will write is switching threshold. So V in switching threshold would be VDD plus 2 upon 3, right? 4, 2. Yeah. So 5 plus 2 by 3. 7 by 3. 7 by 3. 2, 2.67. And that is greater than 2.5 volt. Right? So your switching threshold increased. Right? So basically when V when not V when Kn is greater than Kp, voltage transfer characteristics move away from origin, right? Because at higher value of V in, we will get the switching threshold, right? And when Kn is Kp by 4, what will happen? And mode of Vtp is equals to Vtn. So your V in switching threshold would be VDD VDD plus that is equals to 1 volt. VDD plus 1 by 4 upon not 1 by 4, it would be 1 by 2. 1 plus 1 by 2. That means it would be 5.5 upon 1.5. What look here we have done the mistake. Here this is 2.33, okay, and this is less than 2.5. And we can't really generalize it like if Kn is greater than Kp. It really depends on the formula. Okay, we can't generalize it. Just assume Kn is equals to Just assume Kn is equals to 2 Kp. Kn is twice of Kp. And then try to find the value. So it would be 5 plus root 2 upon 1 plus root 2. And that is greater than 2.5. Okay. So we can't really generalize the formula. We can just write the formula for a specific case that we have seen. Okay. Switching threshold decreased. And when we can't really generalize it, so what we will write, when Kn is equals to 4 Kp. Okay. And in this case 5.5 upon 1.5, it is equals to 3.66, that is equal greater than 2.5. Then switching moves towards here we will write towards, moves towards origin. Okay. Switching threshold increased. Okay. So VTC moves away from origin. Okay. So if there is a VTC drawn like this, V naught by V in. Okay. I will just pause the video and do it. So I didn't make that much wood, but just to make you understand, this is Kn is Kp by 4, right? This is Kn equals to Kp, and that would be Kn equals to 4 Kp, right? Switching threshold is degrees, that means at lesser value of V in, we will get into the saturation region. Here at this value of V in, we will get into the saturation region, and here at this value of V in, we will get into the saturation. Okay, so it is moving this time, it is moving at this side. Okay, so this is what is happening. Okay, so this is the complete analysis. I guess there is no single point is left, so just revise whatever I have told. Okay, so the main curve is this. Okay, so you need to remember, so for 0 to VTN, P is linear, N is cutoff, then one device can't both device situation of both device will not change, only one will change. From linear to linear it is going, from cutoff to saturation it is going, from N is remaining same, saturation to saturation. Now P is changing linear to saturation. Now then P is remaining the same, N is changing from saturation to linear. Okay, then P is changing and N is remaining the same. So P from saturation to cutoff, N is linear to linear. So that you need to remember, concept you know. Okay, the transfer characteristic you know, K and Kp value you know, switching threshold V in value you know. Okay, how does that change, that you know. Okay, so everything you know, and why the PMOS size is larger than NMOS, that also you know. So everything regarding CMOS inverter you know. Now we will just see one more concept, that is the current characteristics. Not characteristic, I would say just the transfer characteristic, one more transfer characteristic. We will draw ID versus V naught. Okay, so from there as well, we will try to analyze something. Okay, and you will see a very interesting concept there. Okay, thank you. Hello everyone. So now we will talk about the current. Okay, so what we need to make is ID versus V naught. Okay, that we are drawing ID versus V naught. This is our task. So for NMOS, V naught is equals to VDS and ID is equals to IDN, right? So for NMOS, V naught versus ID is basically VDS versus ID, and that you already know. Linear saturation, linear sublinear saturation, linear sublinear saturation. V increases, the VDS for saturation decreases, okay, and the uh, value of ID decreases. Sorry, if V increases, value of ID increases, and the saturation point also increases, right? So that you also know, that you already know. But in case of PMOS, there is something. In case of PMOS, what is your V naught? V naught is V. What I can write, your V naught is VDD minus VDS, right? VDD minus VDS, and your I naught is ID is IDP only. So for NMOS, V naught is VDD minus VS. Okay. So for NMOS, we need to do something. So for PMOS, we can draw the transfer characteristic. So PMOS, for PMOS, we will draw it now. Not for PMOS, so for NMOS, sorry. This is for NMOS. So this is ID versus VDS. Okay. ID versus VDS. I don't need to explain it again and again, right? I have already explained it. I have already explained everything, so no need to explain again and again. We will not draw for every case. So let us assume this is for Vin equals to 1 volt. So this will be for Vin equals to 2.5 volt, right? And what will be for Vin equals to 0 volt? This would be for Vin equals to 0 volt, and VDS is here equals to V naught only, right? So this is V naught versus ID curve basically. Now for NMOS, what do we already know? So for NMOS, what do we already know is that here, what did I write? I write VDS now. It should be VSD. So not this, but we will draw like this only. So this is VSD, right? This is VSD versus ID. Okay, we will try to explain it as much as I can. I will try to explain. Okay, so if this is the case, right? This is the case here. Okay, so if so this is the case. This will be V in. Now this will be V in. Now tell me, if V in, the upper one would be larger or lower? See this. If V in is large, your VSG is low. If V in is large, your VSG is low. That means your current is low. If V in is large, your VSG is low. That means your current is low. So the upper one is the lower now. This is 0 volt. This is, let us assume, 2.5 volt. And this would be V in equals to 0 volt. Not 0 volt, 5 volt, because when V in is equals to 5 volt, VSG is 0, that means 0 current is there. So that would be V in equals to 5 volt. Now we have to draw Why I am writing NMOS? Look, I have been decoding for so long right now. That's why it is happening, I guess. So, we are talking about PMOS here, right? ID versus VHD curve. Okay, we are talking about PMOS. Okay, linear and then saturation. But if Vin is very high, that means if Vin is very high, that means your VSG is very low. That means your current is low. If Vin is low, that means your current is high. So that's why I have made the curve like this. Now I have to draw ID versus V naught. Now your V naught is VDD minus VSD. Can you draw the curve of ID versus V naught now? ID versus V naught. In the next page we will make ID versus V naught. ID versus V naught. Okay. So when your V naught is equals to VDD, that means your VSD is equals to 0. V naught equals to VDD, that means your VSD equals to 0. That means your current is 0. So when this V naught equals to VDD, that means your current is 0. And when your V naught is 0, that means your VSD is equals to VDD. Right? Your VSD is equals to VDD. That means whenever the drain potential is low, that means whenever the V naught is low, that means your current is high. So the curve should shift something like this, right? This way it should go, this way it should go, and then there is this, right? Or this way it should go, then this. This will be for V in equals to 0, right? For V in equals to 0, and let us assume V in equals to what we have written 2.5 volt. Okay, so if we have written 0 here, we should write 5 volt here. V in is 5 volt here and 2.5 volt here. Just taking these values 0, 2.5 and 5 only. Okay, so if 0 here, 2.5 volt here, and this one V in equals to 5 volt, right? If V in equals to 5 volt, if V in is equals to 5 volt, then the current is 0. Okay, the current is 0, and whenever your V in is equals to 0 volt, the VSG is 5 volt, that means the current is maximum. And why this curve is from this side? If you can replace it, if you can replace the x-axis, then you can also think like, what is V naught? V naught is VDD minus VSD. So VSD, just invert the VSD, then shift it with VDD. Just take the mirror of this. You need to make minus VSD plus VDD. So take the mirror of this and then shift it by VDD. So we took the mirror of it, then shifted it by VDD. So this is the curve that we are getting, right? So I will write it as well. This is for PMOS only. For PMOS, what is happening is that your V naught is what is your V naught? That is minus VDS plus VDD. Mirrored figure B. This is figure A, and this is figure B. This is figure C. So I mirrored figure B, okay, and added VDD. Now by superimposing, by superimposing figure A and figure C. So by superimposing, what do we get? This is the final transfer characteristic that we get. So this is the final transfer characteristic that we are getting by superimposing both of them. Look, for these curves, these curves are for PMOS and these curves are for NMOS, right? These are for PMOS. Look, in this direction, in this direction, in this direction. So what do we see here? For V equals to 0, this is the curve for V naught, right? For V equals to 1 volt, this is the curve. For V equals to 2.5 volt, this is the curve. For V equals to 4 volt, this is the curve. Now in case of NMOS, it is opposite. For V equals to 5 volt, this is the curve. For V equals to 0 volt, this is the curve. For V equals to 2.5, this is the curve. For V equals to 1 volt, this is the curve. And the VDS value is getting less by time. Okay. So the thing is that this curve is asked in the interview. Okay. I naught versus V naught curve. Okay. I naught versus V naught. Right. Now we can see something here. Look, first thing we are seeing is that when V is equals to 0 volt. Okay. So in case of PMOS, what is the curve for V equals to 0 volt? This is the curve, right? And in case of uh, sorry, in case of NMOS, whenever V is equals to 0, this is the curve. This is in the case of NMOS. I should have written. This is in the case of NMOS. So in case of NMOS, whenever V is equals to 0, that means the current is 0. So this is the curve, right? Whenever V is equals to 0, this is the curve. And in case of PMOS, what is the curve for V equals to 0? This is the curve for V equals to 0. The V is same for PMOS and NMOS. What I will write? V in is same for both PMOS and NMOS in our CMOS inverter, right? In our CMOS inverter, the V is same for both PMOS and NMOS, right? Initially, V is at 0 volt. If V is at 0 volt, this is the case for NMOS and this is the case for PMOS. So at what point the both of the curves are cutting? At this point. So at this point, what is the value of V naught? That is VDD. Take more examples. Take V equals to 1 volt now. V equals to 1 volt. So V equals to 1 volt. This is V equals to 1 volt, right? V equals to 1 volt for NMOS. This is V equals to 1 volt for NMOS, right? For PMOS, what is V equals to 1 volt? This is V equals to 1 volt for PMOS. This is V equals to 1 volt for PMOS. So at what point they are cutting? At what point they are cutting? At this point. At this point. At this point. At this point. What do you see? At this point, what do you see? This is for PMOS. The PMOS is in linear region and the NMOS is in saturation region. When V was 1 volt. Just go to the curve. When V was 1 volt, the PMOS was in linear region, NMOS was in saturation region. Here in the characteristics, you can see that. Right? Here in the characteristics, you can see that when this is the point of this is the point where both of the curves are cutting, right? So this is the PMOS curve. The green one is PMOS curve, right? The green one is PMOS curve. So it is in saturation region, and the this what do we say? Whatever the color it is. So for that it is in linear region, right? Okay, did you understand? Now take V equals to 4 volt. Take V equals to 4 volt. This is V equals to 4 volt, right? This complete is V equals to 4 volt. for NMOS. And for PMOS, what is Vin equals to 4 volt? This is Vin equals to 4 volt. And at what curve it is at this point? At this point, right? So at Vin equals to 4 volt, this is the point, right? So at that point, your NMOS is in linear region and your PMOS is in saturation region. So is that the case? Just see here. For 4 volts, your for 4 volt just before that, your PMOS is in saturation region and your NMOS is in linear region, right? Now for 1 volt we have talked about 1 volt we have talked about, okay. For now talking about 2.5 volt. This curve for 2.5 volt and this is for 2.5 volt. This is cutting right here, right? This is cutting right. This is cutting right here. So what is V0 value? V0 value is something here, right? That is VDD by 2, and both are in saturation region. And in this case for 4 volts, this was cutting here. So what was the VDD value? This. So this was lesser than VDD by this was lesser than VDD by 2. So for V in greater than 4, for V in greater than 4, this was the value we were getting. This was the value of V0 we were getting, and here this was the value of V0 we were getting, right? So for V in equals to 1 volt, we are getting VDD to be high, right? For V in equals to 1 volt, we are getting V0 to be high. This is VDD by 2, right? This is VDD by 2. So for V in equals to 1 volt, we are getting V0 to be high. So by simply this characteristic, we can analyze a complete CMOS inverter. Okay, if I had shown it earlier, you wouldn't understand anything. But now you have seen the complete analysis. You have this curve as well. Just try to analyze this curve as much as you can. Okay, this transfer characteristic is important. Okay, in a very high class interview, this will be asked. Okay, so you can see that for V in equals to 1, your V naught is higher than VDD by 2. Also, you can assume the region of operation as well. That is that your PMOS is in saturation region and your NMOS is in linear region. So this is the complete analysis. So I guess you have understood it. Now you have to revise it completely and it will be all clear to you. A CMOS inverter will be all clear to you. We can see few more questions as well. Okay, we will see that, but it may seem complex to you, but this is a easy topic if you understand it completely. And I have given my best, I guess. Whatever I have, all the logic that I had, all the concept that I could deliver, that I have delivered here. And this current characteristics and all these stuffs, this is like this took me a lot of effort to understand by my own, then to make it work on this writing pad. Okay, so I hope you have understood the concept, and yeah, so now we will move to some questions. Okay, thank you. Hello everyone. Now we will try interchanging the PMOS and NMOS in the CMOS inverter. Okay, so this is the CMOS inverter that we have seen, right? Now we will change the position of NMOS and PMOS. NMOS will be going up and PMOS will come down. Okay, so first thing we need to see is that why do we need a CMOS inverter? What does a CMOS inverter does? For a high output, it gives a low out. For a high input, it gives a low output, and for a low input, it gives a high output. So for a high for a high input, we want output to go all the way down to 0. High input means if we have applied 5 volt here, if it is 5 volt, it is no, from 5 volt we can't start actually. If we have applied 0 volt here, let us assume for a low input, for a low input, we want output to go all the way up to 5 volt, right? If there is low input, that means if there is zero input here, then this PMOS will be on and this NMOS will be off. If this PMOS will be on, then your V output steady state would be 5 volt, right? For a 0 volt input, your V output steady state would be 5 volt. Now, when you have applied a high input, if you have applied a high input, that means your V in is 5, then this will be off and this will be on. Then it will completely be discharged to 0 volt. The thing here is that your V naught steady state, when V in is equals to 0, then your V naught steady state is what? 5 volt. It will be 5 or 4.3. Taking VT to be 1, taking VT to be 1 volt, then it will be 5 volt or 4 volt? 4 volt. Why so? Because the PMOS, the condition for PMOS to be 1 depends on these values, right? And for NMOS to be 1 depends on these values. And this is dependent on the given supply, ground, and the 5 volts and the given input. Okay. So if your input is 5, this capacitor can completely be charged to 5 volt because this is the drain terminal. If it is at 4.3, then your VSD is greater than 0. If it is at 4.4, then your VSD is greater than 0. So till 5 volt it can charge, right? Not 4.3. So it is going all the way up. Okay. And when V in is equals to 5 volt, what will be your V naught steady state? When V in is equal to 5 volt, what will be your V naught steady state? 0 volt or 0.7 volt? 0 volt, because for 5 volt it will always be on. If it is always on, it will go down to the value equals to source voltage. Your VDS has to be greater than 0 for MOS to be on. Your VDS has to be greater than 0. So here your VDS is always greater than 0 until the drain reaches the 0 voltage. So this is the condition. So here in this case, your inverter, in this CMOS inverter, for a high input your output is going all the way down to 0, and for a low input your output is going all the way up to 5 volt, right? Now what happens is that we are interchanging it. Now when V in is equals to not 5 volt, first we will see 0 volt so that the capacitor charges. So when V in is equals to 0 volt, at 0 volt it won't be on, so we will see from V in equals to 5 volt. When V in equals to 5 volt, your NMOS will be on and your PMOS will be off. Now tell me what will be V naught steady state? If it is 5, what will be V naught steady state? Will it be 4.3 volt or 5 volt? 4.3 volt. Let us assume it goes to 4.4 volt. If it goes to 4.4 volt, this is 5, this is 4.4. VG, no, not 4.3. We have taken VT to be 1, right? VT to be 1 volt. We have taken VT to be 1 volt, so it will be 4 volt. So let us assume it goes to 4.1 volt. Let us assume it goes to 4.1 volt. So this is 5 volt, this is 4.1. So this will be 0.9, and at 0.9 it will be off. So it can't really go above from 4 volt. These concepts we have already seen, right? In the capacitor problem, in the biasing problem we have seen MOS biasing. In that chapter we have already seen these problems. So just reminding you that it can't go above 4 volt, right? Because here the condition for MOSFET to be on or off is depending on the source voltage, and that is your output voltage. So your source voltage is getting changed here. So if your source voltage goes above 4 volt, it can't be on. So your V naught steady state is 4 volt. And when V in is equals to 0 volt, your NMOS will be off, right? V naught is and your PMOS will be on. This will be on. Now this is already charged to 4 volt. What will happen? It will get discharged. So it will get discharged to what? It will get discharged to 0 volt or 1 volt? Well, because V in is 0 volt. This is the 0 volt. So it will be discharged to 1 volt only. Let us assume it goes to 0.9 volt. So your VSG would be 0.9. VSG would be 0.9. That is less than mode of VTP. That means that is less than 1 volt. So your MOS will be off, right? So it's not getting discharged to complete 0 volt. So the first thing you notice here is that for a high input, for an input of 5 volt, you are getting a high output. For a high input, V in for equals to 5 volt, you are getting a high output, V not equals to 4 volt. And the second is thing you notice is that you are not even getting the complete output. Like you want your output to go all the way up to, 5 volts, but it is not happening. Okay, so the first thing is that this is not acting like an inverter, because for a high input you would want your output to be low, but for a high input your output is high, right? It's acting like a buffer, not inverter. Okay, and the second thing is that your pull up output doesn't go all the way up to 5 volt and doesn't come down all the way to 0 volt. Okay, so they can ask you this question, why can't we interchange, and when we interchange what would be the analysis, that also they can ask. So these kind of questions can be asked. So now you know the reason, right? The first thing is that it won't act as an inverter. The second thing is that your output is not going all the way up to 5 volt, neither it is coming all the way down to 0 volt. Okay, so I hope you have understood this concept. Okay, thank you. Hello everyone. So from the first video onwards, we were seeing the DC analysis of CMOS inverter. First we applied the pulse input, then we applied the ramp input, then we interchanged CMOS and NMOS. All these things we do. Now we will see the small signal analysis, small signal AC analysis. You can say small signal AC analysis. Okay. So now we have to see the small signal AC analysis. So first thing we will find is that what will be the voltage gain. Voltage gain. Try writing the voltage gain by your own. You can do it now. Okay, so first let us draw the small signal model. This will be shorted, this will be shorted, this will be shorted, and this will also be shorted. This is V, because this is a supply, right? And this VS, why I am shorting this, sorry, this is VS, this is VS, and this is VS, and here we have R not connected, R not 1, let us call it as M2 and M1. So this is R not 2 and this is R not 1. Okay, so this is the thing, right? Now we have two VS voltage, kind of we have two VS voltage, although it is a one supply only. So kind of we have two VS voltage. So we can apply superposition theorem, right? So applying superposition. Applying superposition, what will be your V naught? Your V naught would be V naught by Vs, we will write. Gain equals to V naught by Vs would be, look, first we will consider this one to be short circuited and this one in action. NMOS is in action. Okay, if the NMOS is in action, this is short circuited, so here VSG is 0, right? VSG is 0 volt. If this is 0 volt, then there will be no current, this will be open circuited, right? If this is open circuited, now from V0 to ground we have R01, and from V0 to ground we have R02. So R01 and R02 comes in parallel. So this side is open circuited and this R01 is parallel to R02. So the upper side is gone now. Okay, so now you need to see the lower side only. So what will be the gain for it? This is the common source amplifier, and what is the gain? Minus GM1 into R01 parallel with R02, right? Now in the next stage, what happens is that, oh, we will write it again. Let us erase all these things. You understood, right? VSG is 0, VS is short circuited, VSG is 0. So if VSG is 0, that will be open circuited, R01 and R02 will come in parallel. So your gain would simply become minus GM1 R01 parallel with R02. Okay. So minus GM1 R01 parallel with R02. Now talking about this one, and this is shorted. If this is shorted, this would be gone now because here VGS is 0. So this will be open circuited at 0 current. So this will be open circuited, and this R01 and R02 will come in parallel to each other, right? Because V0 to ground we have R01 and R02. So what will this become? Again, this is the common source amplifier, but this is the case of PMOS, right? In case of PMOS, what will be the current flowing? In this direction, we will have GMVS current, right? Because this is 0, this is Vs. So in case of PMOS, what is the current? GMVSG. What is the value of VSG now? VSG is minus Vs. So GMVSG current is in this direction, GMVSG. What is the value of VSG now? Minus Vs. So GM into Vs current is flowing in opposite direction. So what will be the V0 value here? In this direction, if the current is flowing, so V0 would be minus GM into Vs into resistance R01 parallel with R02. So what is the gain? Minus GM2 into R01 parallel with R02. Did you understand it? Just a simple analysis, nothing else. Again, in case of PMOS as well, it is becoming as a common source amplifier only. Okay. If this is shorted, this is gone. R01 comes in parallel with R02. This is source is common, and we are collecting output at drain. The source is common in case of PMOS. The source is common, and we are collecting output at the drain terminal. So what is happening there? So this is simply a common source amplifier. And what is the gain for common source amplifier? Simply that's same gain. Or I have shown you the derivation as well. The current is GMVS. The current is GMVS in this direction. So your V0 would be minus GMVS into R01 parallel with R02. So this will basically be minus GM2 R01 parallel with R02. Okay. So addition of both. So basically, what is your gain? Gain is minus GM1 plus GM2 into R01 parallel with R02. Okay. Did you get it? Minus sign is common. GM1 plus GM2 into R01 plus R02. So this provides a gain of this much. Okay. So this is the voltage gain. Finding the output resistance. Now you should write it by your own. What is the output resistance? And don't do it wrong this time. Okay. You should be able to write it down correctly. So what will be the output impedance? This VS, everything will be shorted because these are the input source. So this will be shorted. So this will be gone. This MOSFET will completely be gone. This MOSFET will completely be gone. So what will remain? R01 parallel with R02. So it would be R01 parallel with R02. Right? Did you understand it? VS is gone. VSG is gone. VGS is gone. Open circuited. From V0 to ground, what do we see? R01 and R02. So it is R01 parallel with R02. What is input resistance? If input current is 0, then what will be the input resistance? It is infinity, because the input current, this is the input current, this is the input current, these are 0 only, right? So it would be infinity. And what is the current gain? Current gain, I out by I in. It would also be infinity because the input current is 0 only, right? The input current is 0 only. Okay. So this is the small signal analysis of CMOS inverter. Okay. We will see a few more questions now. Okay. Thank you. Hello everyone. So this is the question. You have to analyze the output voltage. This is the configuration CMOS inverter is given, and the thing given is that T is very greater than RC. and this is the input that is given. Vin equals to, Vin is getting from 0 to 5 volt, and then sinusoid input 5 sin omega t basically. Okay, so try analyzing it by your own. Just giving you a hint. Just try to break it in three regions, from 0 to 1 volt, from 1 to 4 volts, and from 4 volts to again 4 volt, because this is sinusoid from 0 to 1, 1 to 4, 4 to 4, 4 to all the way down to -5, and again that. So you have to analyze it for 0 to t. So how you will analyze it? The first condition we can see is that when your Vin is from 0 to 1 volt, and Vin is 0 to 1 volt, okay, this NMOS will be off and PMOS will be on. Now you don't need to, if they are asking about these kind of inputs, you don't need to worry about the condition like PMOS will be on, but will it be linear or saturation? That they don't want to know. They just want to know the steady state output. The steady state output. What will be V0 steady state? If NMOS is off and PMOS is on, what will be V0 steady state? This will be on, and let us assume this is 5 volt only. Okay. So what will be V0 steady state? It will be 5 volt, right? This is 0. This is 0 to 1. Let us assume this is 0.5. This is on. VSG is 4.5. So this is on, and this is off. So if this is on, this capacitor will charge all the way up to 5 volt. So this is the steady state value we need to know. So we will just draw the steady state value. So for Vin equals to 0 to 1 volt, we have V0 equals to 5 volts, right? This is the 5 volt. And secondly, when Vin is greater than 1 and less than 4 volts, okay, so in this condition, from 1 to 4, greater than 1 or equal to 1, so this will be on, this will also be on. PMOS is on, NMOS is on. PMOS is on and NMOS is on. Now if Vin increases, that means if Vin increases, we can do one thing. This we can call IDP, and this we can call IDN, and this we can call IDC. Okay. So if Vin increases, IDN increases, and if Vin is increasing, here VSG value is getting less. VSG is getting less, and here VGS is getting up. Here VGS is getting up. So in case of NMOS, the current increases, but in case of PMOS, your VSG is getting less. If VSG is getting less, that means your current is decreasing, and your IDP is decreasing. So these two things are happening. If Vn is increasing, IDN is increasing, IDP is decreasing. Okay. If IDP is decreasing, that means, let us assume this is 1 ampere, this is 4 ampere. So there has to be 3 ampere current from this side, right? This is 1 ampere, this is 4 ampere. So there has to be 3 ampere current from this side, right? So that's why we have made the direction of IDC like this. So that means your IDC increases, right? That means capacitor starts discharging. So initially it was charged to 5 volt. Now till what value it can discharge? It was charged to 5 volt, right? This was charged to 5 volt. So till what value it can discharge? 0 volt, because this is the CMOS inverter and this is the correct CMOS inverter. And you can also see this is the drain terminal. Okay. So the condition for MOSFET to be on and off doesn't depend on the drain terminal, right? The condition for NMOS or PMOS to be on or off, it doesn't depend on the drain terminal until your VSD or VDS is greater than 0. So if it goes to 0 volt, your VSD would be greater than 0 and your VDS would also be greater than 0 until it goes to 0 volt, right? So from 5 volt to it completely discharges to 0 volt. So that's how it starts, goes down and completely discharges to 0 volt. Yeah, fine. So this is for 1 to 4 volt. Okay. So your V naught steady state would become 0 volt. This is the second one, and now here we will see V in greater than 4 volt and less than 5 volt. Okay, from 4 to 5, what will happen? If it is 4.1, this will be off, your PMOS would be off, and your NMOS would be on. Okay, now if this is on, but what is the value of V naught? V naught is already 0 volt. So what will happen? It will remain at 0 volt only, right? This is off and this is on. There is no supply here. In case of NMOS, there is no supply. This 0 volt will remain at 0 volt only. This is the condition, na? This is the condition. Upper one is off. So if this is at 0 volt, this will remain at 0 volt only, right? So this will remain at 0 volt. So V naught remains at 0 volt. Okay. So this is the condition. And fourth one is if V in is negative. If V in is negative from 4 to 5 volt, that means we have analyzed for this span, right? We have analyzed for this complete half cycle. If V in is negative, then your this will be on. Yeah. If your if your V in is negative, then your PMOS will be on. PMOS on and NMOS is off. That means your V naught steady state would be 5 volts, right? If this is on and this is off, so your V naught steady state would be 5 volt. Okay. Just we are analyzing it for these kind of V in is negative, so it will be V naught steady state would be 5 volt. Okay. So let's see it here. So for this cycle we have seen. After that, your V in is greater than your V in is between 4 to 5 volt. When your V in is between 4 to 5 volt, what is your V naught remains at 0 volt only. So your V naught will remain at 0 volt only. Okay. So your V naught is remaining at 0 volt. Now your V in is between 1 to 4 volt. If your V in is between 1 to 4 volt, what happens is that the capacitor starts discharging. Now we are getting no from 4 to 1 we are going, right? We from 4 to 1 we are going from 4 volt to 1 volt. So for let us assume at 3.9 what will happen? 3.9, this will also be on and this will also be on, right? But the value of V in is getting decreased now. Look, V in is we are going from 4 to 4 volt to 1 volt, right? We are going from 4 volt to 1 volt. So at V in equals to 3.9 volt, both are on, right? PMOS is on and NMOS is also on. Okay. If V in is decreasing, V in is decreasing, if V in is decreasing, then this current in NMOS is decreasing and the current in PMOS is increasing, because if V in is decreasing, then your VSG is increasing. So current in PMOS is increasing and in your NMOS is decreasing. So let us assume this is 4 ampere, this is 1 ampere. So 3 ampere has to go down in this direction, right? Right? So capacitor charges. If your V in is decreasing, that means your IDN is decreasing and your IDP is increasing. That means your capacitor charges. So it's charges and charges up to what volt? 5 volt, right? So from we are coming, this is the fifth condition, from 4 to 1 volt the capacitor charges and it will charge up to 5 volt. So it will charge up to 5 volt. One more thing we can do here is that now if we are coming down from 1 to 0 volt, uh, this is the condition, Vin is coming down to 1 volt to 0 volt. So let us assume 0 volt. So let us assume at 0.9, at 0.9 volt, what will happen? This PMOS is on and this is off. Okay, so if this is on, then your V0 steady state would be 5 volt only. When Vin is 0.9, so this is NMOS is off and your PMOS is on. So here your NMOS is off and your PMOS is on. That means your V0 steady state is 5 volt only, right? And for the negative cycle, what happens? For the negative cycle, V0 steady state is 5 volt only. Now it will always remain at 5 volt till time t. This is the time t. So till time t, it will remain at 5 volt only, right? Did you understand it? Let us call this time t1, t2. These are the time span. So I hope you can see the curve now. Okay. So this is not that complex problem, but just we need to see from 0 to 1 volt we are going, PMOS is on, NMOS is off. So it will remain at 5 volt. From 1 to 4 volt we are coming, from 1 to 4 volt we are going. So both of the transistor are on, PMOS is on, NMOS is on. But you need to see the current. If V increases, your IDN is increasing. That means your capacitor is getting discharged. So it will discharge from 5 to 0 volt only. Okay. Now the third condition is that when we are going for 4 volt to 5 volt, if we are going from 4 to 5, your PMOS is on and PMOS is off and NMOS is on. If NMOS is on, there is no supply, so it will remain at 0 volt only. Now we are uh, from 5 to from 4 to 5, then we are coming from 4 to 5 and then from 5 to 4, right? We are coming down from 5 to 4, then it will remain same only because the PMOS is off and NMOS is on. Now we are coming down from 4 volt to 1 volt. Okay, from 4 volt to 1 volt we are coming down. So at, let us assume at Vin equals to 3.9, what happens? PMOS is on and NMOS is on. So if Vin is decreasing, then your IDN is decreasing, IDP is increasing. Then your capacitor is charging, then it charges from 0 to 5 volt. Then after 1 volt, what is happening? From 1 to 0 volt, both of the NMOS is off and PMOS is on. That means your capacitor charges, so steady state value is 5 volt. So it will remain at 5 volt, and in negative cycle we have already seen your V0 remains at 5 volt only. So this is how it goes. Okay, and this thing that I have written here should not come here. It should come in last, right? Forget that. We will write down here only. What we will write down. This will be the 6th point. If Vin is negative, that means your PMOS is on and your NMOS is off. Then V0 steady state would be 5 volt only. Okay, so this will be 5th and this will be 4th. This should be erased. Okay, so this is the complete analysis. I hope you have understood it. This was a very good question. Okay, thank you.